southern portion.
What?
Is it in Jerusalem or not?
I don't know.
Well,
We're looking at where's Bethlehem?
Yeah.
It's in Jerusalem. It's in Jerusalem.
Jerusalem's a city, man.
These.
Yeah, Jerusalem is a city.
Man, Jerusalem's a city.
Jerusalem is a city.
Oh,
in
it's
Israel.
oh, yeah,
Israel.
Israel. Yeah, sorry. Yeah. So I'm right. It's in Israel, right?
Yeah.
Yeah.
Bethlehem.
Yes.
Before you talk about Bethlehem.
No, Jerusalem's a city. I was wrong about that. Yeah, it's in Israel.
Before you talk about Bethlehem, Pennsylvania.
Oh, no.
No, we're talking about Bethlehem, like
Bethlehem.
yeah, Bethlehem,
Biblical
Bethlehem.
Bethlehem.
Yeah, yes, biblical Bethlehem.
Why?
Oh, someone talked about where Jesus was born, and I said Bethlehem, and then someone said, "Oh, where's that?" And I think it's in Israel.
Yeah.
Yeah.
We were talking about how beautiful Buddhist. Wait.
You were talking how beautiful Buddha
You want to go to Buddhist?
Okay, anyway. Any questions on the assignment? Michael?
Put your mouse one back too.
Okay. So visualize this, right? So here's the wheel, okay? So it's at rest, and we're going to accelerate it for 5 radians per second squared. How long would it take to move through 12 revolutions? So like, I'm going to somehow like hook it up to a motor or something like this, and I'm going to make this thing speed up, okay, at a certain number of radians per second. So it's going to go faster and faster and faster until it's completed 12 revolutions. So first off, what are you going to do with the revolutions? What do you have to change the revolutions into? Radians. One revolution is
2 pi.
2 pi. Okay? So you're going to get the number of radians that the wheel is going to move through. So once you get those number of radians, here's what you have to decide. Is that theta, omega, or alpha?
Theta.
That's your theta, right? Okay, so you got theta. What else do you know? What's the initial angular velocity of the wheel? 0, because it starts from rest. So you know but not equals 0. Okay? It's not moving, it's starting from rest. Okay? So, and you want to find the time, right? So you're going to know theta, but not, and then you also know fish, because you know the rate at which it's sped up, right? So then you go, oh, theta equals 1/2 alpha t squared plus but not time. So you have no but to start with because you're at rest. You know theta because you found that, and you know your acceleration. Find your time. And then once you get that, then there's a couple of different ways you can work it. But, so if all goes well on number 19, your time should be around 5 seconds.
Yes.
Okay, that's an ish. Okay, but around 5 seconds. And then your overall linear velocity, and when you're talking about that linear velocity, that's like how fast like the wheel itself is moving down the road. Okay? So that answer on 19, that last answer should be around 8 meters per second. Okay? That's an ish, but it should be around 8. Your answer to number 20 should be around 20. I'd like to say I had that planned, but I really didn't. Sorry, just not that clever. Now, let's talk about number 5, okay, and 5 and 6. So 5, you're talking about the Earth. So here's one of the things that you have to keep track on 5 and 6. So on 5, you're trying to find omega. So on that one, because the Earth is spinning at a pretty constant speed, which is a good thing, okay? So you're trying to find omega, so you can take theta and divide it by time. So here's the deal. Why didn't I give you the radius when you started to solve problem number 5?
We don't need it.
Doesn't matter. So here's the thing. Whether if the Earth takes 24 hours to spin once on its axis, which it does, or I spin a golf ball really, really slow and it takes 24 hours to spin. A golf ball or the Earth or the solar system, whatever it is, if it completes one revolution in 24 hours, it's going to have the same number of radians per second. So radius is not a factor here. Okay, it's not there.
So no matter where you are on the earth, if you're in Mays, Kansas, if you're at the equator, if you're in the middle of the outback of Australia, doesn't make any difference. This is the great equalizer. Everybody moves through a certain number of radians per second. Okay, it doesn't matter. Everybody's moving at the same number of radians per second. Now, your linear velocity is dependent upon radius. Okay, so this does make a difference in terms of the radius. Well, where are you going to be at on the Earth to have the biggest radius? Where are you going to have the biggest radius? Where would you stand?
Equator.
At the equator. Okay? Because at any other point, if you're at the equator, this is when you have your biggest radius. If you're in Mays, you actually have a smaller radius. And as you go further and further and further north, you actually have a smaller and smaller and smaller radius. So what happens then is that your linear velocity becomes smaller the farther you are from the poles. So this is why when we launched rockets, this is one of the reasons that we chose Cape Canaveral in Florida. Because in terms of the United States, that's as far south as you can go. That was as close to the equator as we could get. So that actually gives us then, because the Earth is spinning, that gives us about 10% of the velocity that we need to launch something into orbit, because the Earth is already spinning. If you really want to maximize it, you go to the equator. There are some companies that, I can't remember which one, they actually build the rocket and launch it from a platform that they drag to the equator. And that way you maximize the rate of spin of the Earth. The hardest place to launch a rocket from is from the North or South Pole, because you don't get any advantage from the Earth is spinning. So then all of your velocity has to come from the rocket engines, and you're not gaining any free velocity from the rotating Earth. Okay? So there's your little rocket science lesson for the day. So, anything else on the assignment?
Number 10.
Okay. So let's talk about number 10. So, here's George. It's his mass, like 56. And then you got Joe over here at 43. So you want to balance this thing out. The total length is 1.75 meters. Now, here's what you can do. Just think this through before you even do anything, okay? Before you do anything. Is that fulcrum going to be closer to George or closer to George or closer to Joe?
George.
Why?
Because he's
He
larger
weighs
mass.
more. So one thing you can do is like, okay, let's just take a shot. Okay, here's just an option. You can say, well, I'm going to guess 0.25 meters. Okay, I'm just going to take a shot. I'm just going to guess 0.25 meters. So you can take 0.25 times the mass of George times G and get a number. Well, then what's left over for Joe? Yeah, so that'd be 1.5, right? So then you can take 1.5 meters times 43 times G, and you can get a number. And see if they're the same number, okay? And if not, then you adjust accordingly. And you can keep going back and forth, and you can narrow it down and just keep guessing different distances. You can do it. I don't recommend it, but it works, okay? Or you can do, oh, we've learned algebra. Oh, that's kind of cool. So what do you want the distance to George to be?
X.
X. What's left over?
1.75 minus X.
Yeah, so you got 56 kilograms, right? Technically times G times X. What does that have to equal?
43 times G times
43
1.75
kilograms
minus
times G times what?
1.75 minus X.
1.75 minus X. Now, this is why you work with numbers. You actually have to multiply by G.
No.
No, the G's actually cancel out. If you did, that's cool, but you don't have to, because they're the same on both sides. So then you just get all your X's on one side and all the other numbers on the other. So if all goes well, now this is what you have to watch. If you work the problem like this, when you find X, what is X measuring? The distance from George. What does the question ask for?
Distance from Joe.
Distance from Joe. But that's an easy fix. Okay?
Just subtract.
Yeah. That's an easy fix. So your answer should be around 1 meter.
Yes.
Should be around 1 meter. Okay. Anything else? Going once, going twice. So, all right. So, if you came to me and you said, okay, let's say hypothetically I ever get to retire, hypothetically, and so this class is set I should just teach until I die.
What? You're retired?
Yeah. Yeah, like just die in class teaching.
Honestly,
Dude, that'd be a way to go out. That's pretty dark.
yeah, like physics and will never be the same. When
Yeah.
you die, you should have your suit just have a ton of physics equations on it.
Have everybody come up to the coffin and write their favorite equation on it?
Yes.
Do you see yourself ever retiring?
I don't know. I at some point I will.
Donate your
Just
body
for
to the
everything
biology
else I still wanna do
department.
in this life. I might join the Peace Corps again and go back to Africa or something.
How upset would you be?
Huh?
How upset would you be if like you did do that whatever, like have them write your favorite formula and I wrote something about biology?
I
He would haunt you.
I would haunt you. Or worse yet, somebody writes the D word.
Uh-oh.
Well, Burkamp, you go into that final deceleration, man.
You'd be seeing Burkamp's ghost.
Oh yeah, I would haunt you from 3.
But not during
Go
Halloween.
back to Africa,
Not during
you should
Halloween.
invite like all your physics students.
Yeah, man.
Oh yeah,
Yeah, not all of them, but like a select, like
the cool ones?
No,
Oh, so you
that's
think
what
you're
I
in that group,
Make
huh?
them not
Oh,
Say, like
yeah.
invite everyone, yes, but then only not everyone's gonna come, obviously.
Yeah.
Dude, I would so go to Africa.
You know, like I'm not. I was not speaking.
Okay. Anyway,
Nick,
back
I'm
to
on
our
your
story.
side.
So if I did retire, hypothetically, or come back from the grave to haunt you, and you said you get to give one lecture out of all the lectures that you get to give, this would be the lecture that I would give, is today's.
Here we go.
Mainly because it's cool because so many kind of random things are going to fit together at the end of this, and it's all going to make sense. Okay. So today's lesson is brought to you by the letter I, which stands for Moment of Inertia. Now, basically, the moment of inertia is a measure of how reluctant an object is to change its angular velocity. Now, remember, with angular velocities, you're talking about a rate of spin. Okay. So basically, if something has a big moment of inertia, that means it's really hard to get it to spin. But once you get it to spin, it's harder to stop. Okay? So like the Earth has a very, very big moment of inertia, which is a good thing. Okay? Because if the Earth had a very small moment of inertia, then it would speed up and slow down very, very easily. Okay? And the Earth has actually slowed down. They think we were initially spinning at about 6. They think it used to take about 6 hours to spin once on its axis. So imagine a day being like 6 hours long. Yeah, it was cool. All in the mail.
That's less than a school day.
Yeah,
That's horrible.
yeah, I know. But we've slowed. Though the Earth wasn't a cool place to be at that point anyway. There was like hot lava.
Yeah, it
and
was
so
real
forth.
hot.
It was not a good place. Okay. Now, here's what's important about this moment of inertia. If you look on the lecture notes that I gave you all yesterday, on the back side, there are a whole bunch of different ways to calculate moment of inertia. Solid sphere, thin hoop, with a certain width of the hoop, whatever, okay? And I would specifically tell you, hey, this is the shape that you have. So, but here's what's important. They all branch off of this idea that moment of inertia is mr squared. Okay, so this is like the broad general idea. So here's what's different than inertia. What's the only thing that affects the inertia of an object?
Mass.
Mass. Okay? That's it. But there's two things that affect moment of inertia. Mass and where that mass is located in terms of the radius. Okay? So there's two qualifying things. So what that means is that I can have two objects of unequal mass that have different inertia, but they can have the same moment of inertia depending upon how I distribute the mass. Okay? Now, let's talk about units. So it's a little bit jacked up, but what are the units going to be for moment of inertia? No.
Kilogram.
Mass this is going to be mass, which is going to be in
Kilogram meters squared.
kilograms, and then you have the R, which is going to be
Meters
so you get
squared.
kilograms
Meters squared.
meters squared. Okay? And no, there's not a cute way to do that. Okay? It's just, that's just it. It's smash mouth units at work, it's kilograms per square. Okay. So, in terms of this equation, I equals mr squared, listen to me, listen to me, listen to me. Even though this is the general idea that we use to model all moments of inertia, you can only use mr squared under two distinct circumstances. If it's a point mass moving around in a circle, or if you are specifically told it is a thin hoop, okay? So anything else, you have to look up the formula. So listen to me. You only use mr squared under two distinct circumstances. Thin hoop or point mass. So an example of a point mass would be like if I take this rubber stopper and I swing this thing around over my head. Okay? So this is a point mass moving around in a circle. Now, the moon, for example, is also a point mass moving around in a circle. The earth is moving around in a circle. So whenever you have a single point mass moving in a circle, you're going to use mr squared. Or if you were specifically told it's a thin hoop.
So like every celestial body?
Yes. That's basically it. Now, with that said, here's the $1 million question. So I'm going to try and balance this rod. Okay? This has two brass weights. I can either try and balance it like this with weights at the bottom, or I can balance it like this with weights at the top. Which one's going to be easier to balance? Weights at the bottom, weights at the top.
Weights at the top.
Top.
So how many vote, some have said top, so how many vote top? How many vote bottom? 3, come up here. You can handle this, I got faith in you.
I know this because I've been really bored in band. So I
Okay.
just take this.
So here's what I want you to do. Hold your hand out, okay? Now take your other hand and study it.
Oh, I'm doing it.
Yeah, no. Take your hand and study it. No, okay, no. Now I want you to try and balance it.
There we go. Oh.
Try and balance it. You can move that hand.
Put it on your fingertip, it'll be easier.
No, it won't.
No.
Yes, it will.
No.
You got weak fingers.
You need a bigger surface there.
Do you want to capture this in the camera?
Okay?
Oh, it's getting caught.
Right, now flip it over.
We need someone to do this. I voted.
What's the term?
That's because she doesn't know how to
Yeah.
balance stuff in her hand.
She looks for so much. I think there's human error involved.
I believe there is as well.
Oh, probably, for sure.
Honest, come and put it on.
No.
Oh yeah.
Never said I was good at
You
it.
said you were bored in band.
Yes,
so-
because we have a big gong mallet, and it's got this big mast at the top, and so we go around it.
Okay, so try.
Eric, stay on camera. Come on.
Oh, stay on camera. Get over here.
Cold.
Okay?
Whoa.
Now flip it over.
I can't do it.
Okay. So, yeah, well, I mean here. Okay?
Oh.
Do it on your chin.
Oh.
Do it on your chin. Balance it on your chin.
Do it the whole class.
No. Okay. Do it the whole.
Balance it on your chin.
Now, why do I lecture? Now, if I try it this way, okay, you can do it, but it's much more difficult.
Might be a hole in the board.
Now, here's the reason why. Look at this equation, I equals mr squared. When I flip it over, what's happened to the radius of where that mass is located?
It's decreased.
It decreases.
Yeah, so my moment of inertia is bigger. So here's the deal. If you're trying to balance it, what do you want the angular velocity of the end of this thing to be? What do you want the angular velocity of the end of this rod to be? 0. You want it to be at rest, right?
Yeah.
Okay? You don't want it going back and forth. So by having that weight out there at the end, then what happens is that this becomes very difficult to make it speed up or slow down. Because it's at rest, that means it's going to want to stay at rest. Now, redo this. Okay? It's simple. All you have to do is hold it like this and go back and forth. Okay? And then flip it over and then do the same thing. Okay? Yeah. Okay? Now, does it feel different?
Yeah, this one's heavy.
It's heavier, right? So by doing it like this, it feels completely different. Because here's the deal. Once that starts to move, it's difficult to stop. Because you have all that weight out there at the end that's moving in this arc. Okay? Got that idea. Now, let's go to the back.
That makes sense, man.
More torque.
Well, yeah, and then if you look at it right, the same reason why we wanted to got the message.
I got it, Max. Yeah, I know. I got it. I know you do, Matt.
Makes sense. I do, by the way.
What? Oh, you did pretty well. I mean, I think I could do better, but
Probably.
you know, whatever. I do a lot of nothing with rakes, so whenever we're raking roots. Landon, don't be in the way.
I am the way.
No, you're not. You are the opposite of that.
What?
The way. He said he was the way.
Okay. So here's what we've got. I've got two. Okay. So I've got two objects that are specifically designed for this demo. They're the exact same width, they're the exact same diameter, and they're the exact same mass. Okay? What changes is the distribution of the mass. So if I put this up here and let go of it, what's it going to begin to do? Okay? Does it undergo angular acceleration?
Yes.
Yes. Right? Because what's my initial angular velocity?
0.
0. So is there a torque applied to it?
Yes.
Yeah, because if I just hold it and I said, hey, you know, Nick, make it spin. Okay, Nick would come up here and he'd grab a hold of it and he'd go, oh, okay, right, I'm going to apply a torque to it. Okay? So when I let go of it, it begins to spin. But if I set it here, nothing happens. What's the difference? What about it? Oh, okay. So force parallel is trying to drag it down. So, when I look at this, if this was the magic frictionless inclined plane, and I even set it down here like this, if this was frictionless, what would it start to do? It would start to slide. Now, if this was still the magic frictionless inclined plane, and I put it here like this and let go of it, what would it do?
Slide.
But would it rotate?
No.
No. Okay? It would just go down here like this. So, but here's what's cool. You'll notice that it rotates in the opposite direction of motion. Okay? So it's going down like this, but it's actually spinning in that direction. So what's the direction of the force creating the torque? When I let go of it, is that force acting up or down the inclined plane? Up. And that's why it's spinning that way. Just like if I hold it like this and I said, hey, Nick, I need you to make it spin in this direction. Okay, Nick would apply a force this way. So you have two things that are happening. You have force parallel, which is trying to drag it down, and then you have friction, which is acting to make it spin.
So is it acting as a torque?
Yes.
Okay.
Yeah, so those two together. So gravity, force parallel, is making it pull down. And then friction with that surface is creating the force that's going to make it spin. So here's what we're going to do. I'm going to set this up like this. And we're going to have a race.
A little race here.
Okay, a little race.
Little race.
So, one of three things could happen. Keep in mind these are the exact same, they're the exact same mass. Even though the materials are different, it's basically the same frictional force. Okay? There's enough to make them both spin. So here's the $1 million question. There's three options. The Lord of the Rings could win. The hockey puck could win. Or it's a tie. Those are your three options.
I want the Lord. I want the Lord.
Lord of the Rings.
So, how many vote hockey puck?
Air has to do with it.
1, 2, 3, 4.
I think
Okay.
it's the Lord of the
Wait,
Rings.
you voted
How many
hockey puck?
vote Lord of the Rings?
For sure.
There's more mass.
For sure.
On the outside,
Okay.
exactly. So it
How
takes
about
more force
Lord of the
to
Rings is a slight
No, it has
advantage?
more
How about it's just going to be a
pushing.
tie?
Michael.
Michael
Yes.
votes tie.
Watch him do
See the brakes.
Okay, get off of the table.
All right.
Get
No.
your feet off the table.
Hold on, different.
She kicked the thing over.
He made me angry.
I
So
made her
you kicked
angry
my
because I'm
camera?
right, so she
No,
kicked
I
the camera.
moved to kick him and I missed.
Okay, she was not trying to kick me. She's just bad.
Don't get Stan Burke.
Okay.
Right there.
You win this
I
time.
knew it. You know why I knew
You
that?
win
Why
this
did you know that?
Because hockey players, why would they use that if that was faster? They would
You realize hockey pucks don't roll on
And
the
that's what
ice.
That's actually like that's the stupidest thing.
Yeah. Now, let's just make sure that it isn't just because that's like one side of the table versus the other. So we'll put them on the other side, right? We'll do it again, just
They have
make
the
sure
same
that the side of
There's
the
more
board
mass on
wasn't
the
a
edge,
contributing
so there's more
factor.
inertia on the edge.
Okay?
So you need to apply more torque to roll the same.
If that metal one, the hollow one, is faster, hockey players would use that.
But they're not rolling.
Okay,
You're not rolling.
it doesn't roll!
That's the point. All right. That's
You're the smartest human being I know.
Okay.
Frictionless surface.
Yeah. Okay. Now, here's the deal. Why did the Lord of the Rings make it slower, and why did this one accelerate faster?
You took more forces to go.
There's
Okay,
more
hold
mass
on.
on the outside.
Okay, let's talk moment of inertia. Let's talk moment of inertia. So, if you consider this being a uniform sphere, so like on average, imagine that all of that mass is concentrated halfway between the center and the outside. So on average, that's where that mass is located, okay, because it's an even distribution. This one, you have that mass all the way out on the outside. So imagine this being like, you know, what Bree did with the rod and the weights. So imagine that you have a whole bunch of these built like this, and it's one continuous thing. So with this one, you have all of this mass out here on the outside. So this one on average has a much bigger radius. So what that means is that this has a bigger moment of inertia. So it's more reluctant to get sped up. But if I got them going and rolled them, which one would roll further?
The ring.
The ring would. Why?
Because it has more.
Yeah, because it's going to be harder to stop. Okay, so if they're both going, the Lord of the Rings would roll further. Now, take a couple of these, put it up here.
What we got here?
I don't know yet.
We're kind of take one.
Whoa! Ran him off the track.
He'll experiment.
We'll get 2 timers for better data.
Here we go. Fair race.
Okay, now, open that one up.
2.13. I did for the tape.
Okay. Whoa. So, they both have four ball bearings. This one has 4 ball bearings around the outside. That one has 4 ball bearings on the inside. So, which one has the bigger moment of inertia?
The one with the outside.
Outside.
This one does, right?
See.
So, that's why this one wasn't going as fast as that one was. Because on average, that mass is located to the inside. So, this is what you have to understand so far. The smaller the moment of inertia, the easier it is to get it to speed up. Now, by the way, you all did much better in opening that because I gave that same challenge to my first block class, and I swear to God, they had to pass it around to 6 different people before they could figure out how to take the wing nut off that. So,
You mean unscrew it?
Lefty loosey.
I know, but I swear to God, it like started here and it got to 6 different people before they figured out how to get it undone.
Who were those people?
I'm not going to say.
Okay.
Please.
Okay?
One of them Nugget?
No.
If you did, it
I'm
might
not
make
gonna
more
say.
sense.
That was Cam, wasn't it?
All I'm saying is that if you know people in my first block class, just ask them about the wing nut.
I'm gonna ask him.
Who got it off?
I can't say.
I'll
Okay.
just ask
The
him.
chase.
Now, then you could have a
I bet Chase
situation like
was
this.
angry. He was like,
Whoa!
Whoa.
That's not right.
Perfect.
Stripping.
That is magic.
Heads
That's
up.
crazy.
Heads up. It's
That's
not even a blue, is
magic.
it?
That's
Wow.
crazy.
That's magic.
It's like the
But if I go like this,
Oh, you put it all inside, didn't you? Skip you
yeah,
low.
so this one I've got all of the weights concentrated on
One side.
one side.
Huh.
Huh. Should erase that one. Yeah, how that would go. So with this one, this is how you can make it roll uphill. Is because if I position it just right, all of that weight, okay, is like sitting up here. Gravity is pulling it down basically on this side, and it rolls back uphill. But that's also why it becomes stationary. But if I get it where it's going to go just over center, then it starts rolling downhill. So this is kind of like the drunk version, you know. Whoa, whoa, okay. Or you can do like magic and it goes whoa, up the hill. Okay, got this idea? Got it? Good? Back we go. Back we go.
Oh God! You made me angry, and I tried to kick you, but I just hit the camera.
I'm not even asking.
Oh man. Feelings.
Thank you. Yeah.
We are at 21
You're
minutes.
fine.
Are we gonna have 40 more minutes of lecture?
What?
Are we gonna have 40 more minutes of lecture, at least? Well, we're at 21 minutes, so I can't even count that high.
1, 2, 7.
No, it's
Okay.
5.
So, of the two,
She put tape in her hair.
she put what?
Tape.
Fight it out. Fight it out.
Okay.
This is why you shave your head.
So,
Yes.
no.
Please don't look at me that
So-
disapprovingly.
Here's the deal. So when we set them on the inclined plane, which one made it down first? The disc or the ring?
This.
The disc did. So what that means is that that one underwent a larger angular acceleration. So this had a bigger fish, this one had a smaller fish. Okay? Now, which one had the bigger moment of inertia? The ring or the disc?
The ring.
This one had a bigger eye, this one had a smaller eye. Okay? So here's how you remember this, is that big fish have small eyes. Oh! Okay? That's pretty good. That's why I make the big money. Okay? So, big fish have small eyes. So the converse of that is that if you have a small fish, it has a big eye. So graphically, if you want
Goldfish.
so this is just like one big eye, right? And this one just has like this tiny little eye. So here's what's important. There's an inverse relationship. So the bigger the moment of inertia is, now this is a huge caveat, and you'll see why this works in just a second. If you apply the same torque, the one with the smaller moment of inertia will accelerate faster. Okay, it's one of the key things that you have to understand. Now, don't write this down. I'm just showing you why the math works. Okay, what I'm going to write down, you don't have to write down unless you're just really hardcore and crunching numbers.
You said the one with the smaller,
Huh?
the one with the smaller moment of inertia.
The bigger angular acceleration.
Don't make it good. Better be something.
Yes. I don't know. I thought I felt something hit my chest.
Are you okay?
Good and Matt. There's like hot chocolate stuck on the edges of my lips. I didn't realize that. Yeah. I'm like scraping it off I'm like scraping the skin off and hot chocolate, something like that.
It's pretty gross.
Yeah, it's pretty gross. Is it still there? Like on the edge? What you got in here? Hot chocolate. You want to take a sip? No. Why not?
Hot chocolate from my thermos.
What do you mean? No, it's It's not like difficult to clean though. It only has like 2 parts. It seems like that's it. It's easy to clean. There are some that are like impossible to clean, like those ones. This one. That's hard. Those are hard to clean. It doesn't smell that great. I'm gonna put tea in it for the game.
Okay. So don't worry about this. All I'm showing you is 2 different examples of the formulas that you use. So with Lord of the Rings, basically you had 2 radii, an inside radius and an outside radius. So if you're not sure which formula to use, look at the information that you're given. If you're given a mass and 2 different radii, then when you look at on the back of the lecture notes, you're going to find a formula that involves those numbers. Okay? That's how you know which one to use. So don't memorize these. I will never expect you to have them memorized for the test. I will always give them to you. You just have to know how to use them. And they're also on the equation sheet itself. So if you look on the back of your equation sheet, the big dog equation sheet, there's all these formulas for moments of inertia. Yes.
I thought we were looking at the.
Well, no, there are, but they're also on your equation sheet as well. Okay? So that's more of a visual kind of way that's listed. Now, here's the weird thing about moment of inertia, is that you can't directly measure it. Okay? There is not a moment of inertia sensor that exists in the world. Okay? It isn't like, oh, I'll go get the moment of inertia scale, and we'll take it, we'll set it on there, and we'll go, oh, here's the moment of inertia. Okay? You can't. You can work out the math, and typically if you go through calculus, usually Calc 3, maybe differential equations, is when you actually come up and you derive all of these equations, and that's where they all come from. Some of them get really, really weird. But this is the simplest to kind of conceptually understand. So if it's a solid disk, and this is the one that you would see probably most often is the moment of inertia of a solid disk, is it's 1/2 mr squared. So if you contrast that with a thin hoop moment of inertia is mr squared because you have all of that mass concentrated around the outside. If it's a solid disk, we're saying that on average, that material is halfway between the center and the outside edge. Okay? So that's why this is 1/2 mr squared, and if it's a thin hoop, it's mr squared. So here's all I want you to get out of this. The moment of inertia of that solid disk is 1.8 times 10 to the negative third. The moment of inertia of this one is 3.4 times 10 to the negative third. So the moment of inertia of that solid disk was smaller than the moment of inertia of the Lord of the Rings. So that's why when you applied the same torque, this one underwent a greater angular acceleration. Cool with this. Okay? Don't write this down. I'm just showing you how you calculate. Okay. Now, next thing. When you talk about things that spin, okay? Here's the one equation. I'm going to use it, but don't. Here's the one equation you are forbidden to use when you talk about making things spin. And that's F equals ma. You are absolutely forbidden for using F equals ma. And here's the reason why. I can use F equals ma if I'm just going to take this wheel and I'm just going to throw it to my griddle. Okay? If I'm not making it spin and I'm just throwing it, I can use F equals ma. Okay? Mass, acceleration, not a big deal. But here's why you can't use F equals ma if you're talking about something spinning. Because if I take this wheel and I apply a force right here close to the center, I get a certain acceleration. If I apply that same force out here on the edge, I get a completely different acceleration. So this is why you can't use F equals ma. Because where you apply it creates different amounts of torque. And that torque then is going to produce a different angular acceleration, which is going to produce a different linear acceleration. So if you're talking about something that's spinning, and you find yourself trying to use F equals ma, stop. Phone a friend, get help. Don't do it. Now, as I say that, I'm going to violate my own rule momentarily, and I'm going to use F equals ma. But it's okay, it'll be all right in the end. So yesterday, we established that torque equals force times radius. True? So we came up with yesterday.
Yeah.
Now, since the day that you've been in this class, you also learned that F equals ma. So what I'm going to do is momentarily, I'm going to take ma and I'm going to substitute that in there for force. Momentarily. Okay? Momentarily. So I'm going to have mar, right? But here's the problem. I'm going to make this wheel accelerate, but I don't have any linear acceleration. So I've got the only acceleration I have is angular acceleration. So here's the question. What's the relationship between linear acceleration and angular acceleration, which is alpha?
Radius times
A equals
radius times alpha.
R alpha. So can I take R alpha and put that in for A? I think that's reasonable. So then I get M R alpha R, right? Go with this. But if I take R times R, I get
R squared.
MR squared alpha. But what did we say MR squared was equal to? Moment of inertia. So that's also I fish. Okay? So torque equals two things. It equals force times radius, and it also equals I fish. Now, here's why this works. So because torque equals I fish, so let's go back and look at what we just said. Torque equals I fish. So when you had the solid disk, right, versus the Lord of the Rings, which one had a bigger moment of inertia? Lord of the Rings or the solid disk?
Lord of the Rings.
Lord of the Rings. So the Lord of the Rings with the same torque, this one had a bigger eye, so it had a smaller fish. This one had a smaller eye, but it ended up with a bigger fish. Okay? So that's assuming that I'm applying the same torque to both of them. So if the same torque is applied, the one that has the bigger moment of inertia is going to have the smaller angular acceleration. Now, here's the deal. This only works if, number one, it works mathematically. Number two, it also only works if the units work out. So let's see if the units work out. So I've got torque equals two things. It equals force times radius. It equals I alpha, right? So this is what we've established. It equals two things. So let's start with this side. What units is any moment of inertia going to be measured in?
Kilograms meters squared.
Kilograms meters squared. True? What's alpha measured in?
Radians per second squared.
Radians per second squared. The radians are like this ghost thing. They kind of float in and they float out, right? So basically I get kilograms meters squared over second squared, right? So that's what that left side breaks down to. Now, over here, I've got Newton meters. But what can I do for the newtons?
Kilograms meters per second squared.
I can do kilograms meters per second squared, but I'm multiplying that by meters. So oddly enough, on both sides, got kilograms meters squared over second squared. So I can't have one equation producing one set of units and then the other equality producing something else. They have to produce the same thing. Otherwise, the equation isn't valid. So let's look at this. So if I take this wheel, okay, and here's what you want to focus on. So I got the wheel, it's at rest. And then I'm going to make it spin. By making it spin, what have I done to the moment of inertia? What have I done to the moment of inertia by making it spin?
Nothing.
Absolutely nothing. Why? What's the only thing that determines moment of inertia?
Mass and radius.
Mass and radius. Is spinning a factor?
No.
No, it's not a factor, right? Now, does this wheel have a moment of inertia?
Yes.
Does it have mass?
Yes.
Yeah, trust me it does. Have radius?
Yeah.
I think so, right? So I have mass and I have radius. Okay, here we're off to the races. Cool. Okay? So, and this is actually has this weight concentrated toward the outside. So this actually has a relatively big moment of inertia because that mass is concentrated towards the outside. So here's what you want to look at, and this is why this works. If I take my finger and I apply a force right here towards the center, I get a certain amount, I get a certain fish, right? If I apply that same force out here on the edge, I get a much bigger fish. So why do I get a bigger fish by applying the force out on the edge?
Like the same thing with the door yesterday.
Radius is bigger.
Same idea,
Your torque is.
because torque equals two things, right? Torque equals, hold on, hold on. Torque equals two things. It equals force times radius, and it equals I fish, right? So here's the wheel. So when I apply that force, and this is assuming that here's what's important. You have to focus on what you're holding constant. Okay, that's vital. You have to focus on what you're holding constant. So if I apply that force right here, okay, what's happening to the radius? Small radius. So same force, but a small radius. Now, is that going to alter this moment of inertia where I applied the force?
Yes. No.
What determines this moment of inertia?
Mass.
The mass and
Radius.
the radius. But that's the radius of the mass. It isn't where I'm applying the force. Okay? Even though we are talking about radii, we're talking about two completely different things. Okay? One's for mass, one's where you're applying a force. So, over here, I've got the same I, but with a small radius, then I'm going to have a small fish.
Okay, sorry.
Because I'm not generating very much torque. So I don't have very much of an acceleration. Now, if I apply that force way out here on the edge, I've got the same force, right? But now what's happened to my radius? Now I've got a bigger radius, but I've got the same size I, but now what's going to happen to the fish? Now I'm going to have a big fish. So I'm keeping the force and I the same. So as I increase the radius, I increase the fish. Makes sense? Okay. Now, with that said, here's the last thing to introduce. L equals I omega, or I button. Momentum. Okay, so let's look at a couple of situations. Here's the equation that we already talked about, linear momentum, mass times velocity, okay? So here's what's important in this. If you think about it, what you're multiplying by is mass and velocity. Mass is a measure of resistance to a change in speed. If it's objects at rest, it wants to remain at rest. In motion, it wants to remain in motion. This is how fast you're moving. So basically, this is inertia times how fast you're moving. And that's what mass is measuring. And then you get your momentum out of that. So if you look at angular momentum, you're multiplying together the same concepts. Okay? If you think about it, you're multiplying the same concepts. This is your moment of inertia. This is a resistance to a change in your angular velocity. This is how fast you're spinning. So in both cases, you're multiplying a resistance to a change in motion by how fast you're spinning. Now, the same thing is true. If I'm not spinning, what's my angular momentum?
0.
0. Okay? But as soon as, if I take my chair right and I begin to spin, as soon as I spin, now I have angular momentum. But if I'm just sitting here, I don't have any. So the same thing is true of linear momentum. If the 1 kilogram mass is at rest, it doesn't have any momentum. If I begin to move it, oh, then it has momentum. So it's the same type of deal. So we have L equals I but, P equals mv. Is linear momentum always conserved?
Yes.
Yes, it's one of the great conservation laws, right? Linear momentum is always conserved. So if linear momentum is conserved, guess what?
So I'm saying
Angular.
Angular momentum will be conserved.
all momentum will always be over.
Oh, nice. Okay. So, Mary, come up here. You can handle this. I got faith in you. So, we're going to have Mary stand on, might have to do a little camera work in that next. We're going to have Mary stand on what's known as the green spinny thing. It has this green and it spins. Okay? So, stand on that. Now you're fine. Okay, hold these. Okay. Now, here's the question. Does Mary have a moment of inertia?
Yes.
Yes, why?
Because
Yeah.
there's mass and radius.
She has mass and she has a radius. Now, is it possible for Mary to change her moment of inertia?
Yes.
What can she do, Shively? If I wanted her to have a bigger moment of inertia, what could she do?
Straighten her arms out.
Yeah. So, or if you put them out like this, right? So if she moves her arms out like this, has she changed her mass?
No.
Maddie.
But so she hasn't changed her inertia. But what has she changed?
Get out
Her
of
moment of
Bird's
inertia,
face.
right? So when she has her arms out, she has a bigger or smaller eye. When she has her arms out, bigger eye. Why?
Bigger resistance to changing.
Yeah, a bigger radius, right? That's the whole key. She has a bigger radius, so she's going to have a bigger moment of inertia. So when she brings them close, right, she's going to have a smaller eye, okay? So she can change her eye based upon the distribution of mass. Can she change her can she change her inertia?
No.
Because that's only dependent upon
Mass.
mass. Okay, now here's what I want you to do what you were doing before. Okay? So I want you to take like the top half of your body and twist it one way, and then I want to see what happens with the rest of you. Okay? Now, just kind of go back and forth like this. No, just kind of go like this. Yeah, kind of do the twist thing. Okay? Now, I don't want you
Go to both sides.
No, go
Don't let
both
it-
directions. Yeah.
So back and forth.
Like do it
No,
back
like just
like
yeah,
this.
just go like that.
yeah, like that.
Okay, that's it. Beautiful. Beautiful. Okay, now stop. Okay. So if Mary takes the top half of her torso and goes to her left, what does the bottom half of her do?
Go to the right.
Goes to the right.
Oh.
Why?
Equal and opposite reaction.
Kinda. Does momentum have to
Oh,
be
it
conserved?
has to be
Yeah.
0, so you have momentum going this way, which means you have to have some going that way.
Yes.
The
So
glasses.
that's like a cannon and a cannonball. When you fire a cannon out of a cannonball, what happens?
Cannonball.
Cannonball goes one way,
Cannon goes that way.
back.
right?
Like it's-
So that's what happens here. She has no angular momentum. So when she twists one way, guess what?
Twist the other.
The bottom has to go in the opposite direction so that everything still adds up to 0. Okay? Now, how's your sense of balance?
Not great.
Really? Seriously? Yeah. Okay, we're not going to have you do the next part then. Okay. So, how's your sense?
No, I'm bad.
No?
I got
Bree?
9.
And mine like that.
Have Vonda do it.
Oh no. Don't.
Fonda! No? Come on, Rhonda!
Actually, yeah. Let's see if she'll fall
Gymnast
in.
or something.
Oh, we should have made Mary do it. It would have been way funnier.
No, she'll actually hurt herself. Her balance is
Yeah.
so bad.
And like, I'm
Well, of course,
And-
the next
so
one.
much.
Okay. Okay, so here's what I'm going to have you do. Okay, hold these. All right, so here's what I'm going to have. Here's what we're going to do with Vonda. You're going to have your arms out, okay? And I'm going to make you spin, okay? Then I want you to take those weights and bring them
Oh, and then I
in.
go faster and slower. Alright.
Oh, okay, you ready?
But they messed up.
So I want to apply a torque. No, okay. Keep them out, keep them out. Now bring them in. Now back out. Okay, no. Not that fast. Okay. Okay, try it again.
Alright, I'm ready.
Okay, ready? Now bring it in. Ooh, that was nice.
I did that.
Okay, now, Tori, come up here. Come on.
Sorry.
Yep,
You probably have the best sense
come
of
on.
balance.
That's a good bed. That's chocolate.
Come on. I got faith in you.
Knock your head on that.
Now, I want to do the same thing, but I want you to take them and put them up over your head.
Okay.
Okay?
Yeah.
Got it?
Ballerina.
Yes. Okay. No, start with them out. Okay? All right, you ready? Woo! Okay?
Quick.
That was nice.
Yeah.
Now, next time I want you to do that, then I want you to bring them back down.
So start up.
Yep, no, start out, start with them out, bring them up, and then back out. Okay, ready?
Yeah. When they're spinning like this. Yeah.
Nice!
It's like the Olympics.
Oh, it's like the Olympics!
When you see the ballerinas go like that, and they go faster and they put them out.
Or the
they
figure
go-
skaters.
Exactly.
The figure skaters.
It's in the Olympics.
Okay, well done, that was nice.
He was right about. He was right about.
All right.
Yeah, he was right. He was right about the physics part, just not the common sense part.
So, here's the deal. So, we'll look at Tori, okay? So, she was here and she had her arms out, right?
Big ol'
Okay?
hands.
The glass.
Right? Had her arms out. So, sorry, your hands, those are weights. Okay, don't. Oh, you drew, no. Okay. So, when she was spinning, oh, here, put the bow over here. Okay. All right. So, when she was spinning, did she have angular momentum?
Yeah.
Yes.
Yes, right? So she had a certain value of L. When her arms were out, okay, what happened to her moment of inertia?
It was
Bigger.
Bigger, right? So she had a big moment of inertia because she had a big radius.
Makes a smaller acceleration.
But she was spinning slower, right? Don't throw acceleration into this, okay? We'll get to that. So she was spinning slower, right? Now, when she took them and took those weights, right, and she put them up over her head, okay, like that. My apologies, Tori. I teach physics, not art, okay? So when she did this, okay, let's look slower. Okay, but you got the idea, okay, you've got the idea. So when she did this, what happened to her moment of inertia? It got smaller. So she had a smaller eye, but then here's what's important. We had to conserve angular momentum. So what happened to the value of the rate of her spin?
It went up.
It got bigger. So if you want a small butt, you want a big eye. If you want a big butt, you're going to have a small eye. Okay? Because you always produce the same value of L. Now, here's the cool thing. To a certain extent, you can make the argument that this is sorcery. Okay? Now, even though you don't have good sense of balance, we can do this thing. Come up here. There.
I'm sorry, it's the last class. You should have done this last night. Don't get
Now,
mad
kind
at
of sit like Indian style.
me. Well, don't get mad at me for you not doing your homework.
Crisscross.
That's not the reason why I'm mad.
Okay. Now, you can do this. It's not as dramatic, but you get the idea. So, have your arms out. Now, I'm going to apply torque to Madeline. I'm going to make her spin, right? Okay, you ready? So, you go like this. Now, bring them in. Now, back out. Back in. Okay? So, you can even do it sitting in a chair like this. So, when that happens, here's what, if you look at, like, oh, it's magic. Because she is changing her speed, but nothing is touching her. So if the definition of magic is something happening without any physical contact, that's sorcery. Because you're a witch, okay? So she can make herself spin faster or slower by changing the distribution of mass. We'll do it again. Okay, ready? Okay, go fast. Arms out. Okay? So you can actually see her spin faster when she brings those in. Okay? And then change back out. What?
What was the noise she made?
She's a witch. She can get away with it, okay? She'll put a curse on you and make all that
And we
hair
can get
fall
away
out.
with burning her.
She'll turn you into a newt.
Whoa, that's a bit harsh.
No.
And a curse isn't?
Okay. Thank you. Okay.
On the stage.
Now, here's the odd thing about momentum, angular momentum, is that it has a direction. Now, this is where it gets weird in terms of the direction. So if I have a golf ball and it's moving in this direction, which direction do you think the momentum vector points? That way. If the ball is going up, it points up, right? So the linear momentum vector points in the direction that the object is going. Not a big deal, right? But angular momentum gets a little bit weird. So, what do you come up here?
I have to. Oh, we're lucky it's Bree. Now I
So
don't
now
have
we're
to
going to
lift
use
it up.
bicycle wheel and brake. So stand on the green spinny thing.
Are we gonna spin the ball?
Okay, got it. Arms out. All the way out like this. Okay, now, how much angular momentum does the wheel have right now?
Zero.
Zero. What about Bree?
Zero.
Zero. Now, to find the direction of your angular momentum vector, you use what's known as the right-hand rule. So, hold that out. So, I'm going to make the wheel go in this direction. So, what you do is you take your right hand, hence the term right-hand rule, and you curl your fingers in the direction that it's going. The direction that your thumb points is the direction of your momentum vector. Okay? It works. You'll see why. Okay? So, when this is going in this direction, you curl your hand this way, your thumb points in that direction. Now, if I reverse it and make it spin the other way, then you take your right hand and you curl it this way, and the momentum vector points to the right.
Talking about grabbing it?
No, you're not actually grabbing it, okay? You're just taking your hand and you're curling it in the direction that the wheel is moving,
Oh.
okay? So if the wheel is moving this way,
Point that way.
points that way. But if it's in the opposite direction,
Brush up on it. slow
yes.
down.
Now, just like Bree, if I take Bree and I spin her in this direction, then I would wrap my fingers in the direction that she is spinning, and the momentum vector would point up. If she's spinning in the opposite direction, then I would take my hand, curl it in that direction, and the momentum vector would point down. Okay?
So how does
Now,
that make sense?
here's what we're going to do. I'm going to get this
No.
spinning. You need to hold it out, and then I want you to like tilt it like over like 90 degrees, and then I want you to stop and then turn it back the other way. Okay, you got it? I got all the faith in the world. You ready? Okay, now lay it over.
Just going this way.
Okay, now roll it back the other way.
There we go.
Now, like I'm thinking like roll all the way over.
Now, like
Yeah.
a car.
Okay, okay, now.
Whoa.
So, here's the deal. Why is she moving when she tilts the wheel?
Oh.
Oh, almost. Let me try to get it a little bit faster. But this time, I mean go like all the way like this.
Oh, like turn all the way?
Yes.
Okay.
Okay, you ready?
Did you not say that like 6 times?
Okay. Now go back the other way. Okay? So, here's the deal. So why does she move when she tilts the wheel? Because what has to be conserved?
Momentum.
Angular momentum. Whoa.
Once
Once you get the hang of it, you can actually,
Whoa. She's drifting.
whoa, she's drifted. Okay. Got it? Okay.
Dude, it's fun.
Can I see grape try?
You want to try it, Ray?
I want to try it.
Okay.
Yes.
Give you a spin.
Oh, Bree, get out of the way.
Oh my
God. Down in.
There we go.
Make sure they get the whole outfit.
Yeah, they got that outfit.
That's it.
No, keep going.
Turn it the other way.
Whoa.
No.
No, turn it the other way.
Wait, why is it not working for
No, tilt it. Okay, bad.
Oh.
Tilt it over.
Here we go.
Not the other way.
Oh.
You're really good at this.
No, he's not. He was much better.
Here we go.
You're just moving it yourself, man.
Let's try you in the chair. Let's try you in the chair.
I can feel it working.
Okay, now make sure your feet aren't on the. Okay, you ready?
Oh, I'm nervous now.
Now, roll it back the other way. Like
Don't angle, yeah.
Yeah.
Right.
Just like drop your
Yeah,
shoulder.
like that.
Okay.
I have lost
Huh? Well,
because you're not doing it right.
it worked fine for Bree.
You're not working.
Okay.
Oh.
You want me to do it again?
Yeah.
Okay.
Okay, yeah, let's see how she does it. I need to watch the game.
Okay, watch, go back and watch game tape. You ready?
Spinning it. Okay. Oh. She's alright. I think I was in
Okay. So here's the deal. What is she doing? Whoa. That was almost out of control. Okay. Okay. So what was she doing when she tilted it? What did she change? Did she change the magnitude of the momentum vector?
No.
But she changed
What did she change?
Direction.
She changed the direction of it.
Yeah.
So when she changed the direction of the momentum vector of the wheel, her momentum vector had to change to make up for that. So this is how gyroscopes work in navigation systems like on spaceships, right, or airplanes. Because you have a fast spinning object, right, and that wants to maintain a certain angular momentum. So this is why, if you've ever tried to ride a bicycle, if I try and balance this like this, okay, it doesn't stay up because it doesn't have a momentum vector. But if I get this thing spinning, okay, then it stays upright because this wheel is going in this direction. So now that momentum vector, now it has a momentum vector, and that momentum vector doesn't want to change. Now, as it slows down, what happens to the magnitude of the momentum vector?
Decreases.
It becomes less because it's not spinning as fast, right? Yeah. If I spin it the other way,
See? That's not how a helicopter works.
if I spin it the other way,
What's up with you in describing how helicopters work 100% incorrectly?
that's kind of how a helicopter works.
Yeah, see, give
Okay.
the man some credit.
Like how a top works.
Okay, they're validated? Okay, so stop the camera.
Oh
Let me
man,
hand
we're
out
only
the sign.
3 minutes short.
Oh,
No, we're not done yet. Hold on, we'll get there.
But on this one recording, like, whatever. there it is. But-
Okay, so here's the deal. So let me kind of get you through some of these. So refer to that sheet that has all of your different moments of inertia calculations. So like on number 1, you've got a solid cylinder. You're going to find a solid cylinder as 1/2 mr squared. And then you've got a hollow cylinder with the same radius as number 1. That one you're going to use 1/2 r1 squared plus r2 squared. Okay. On number 5 through 10, you're back to a solid cylinder. On number 5 through 10, keep in mind torque equals two things. It equals force times radius, and it equals I alpha. Okay? And you got to use both relationships. On 5 through 10, do not, for the love of physics, use F equals ma. Okay? Do not, on 5 through 10, use F equals ma. Now, when you get to number 16, okay? So let me point out what's going to happen on 16. You got a hollow sphere, and that's 2/3 mr squared. That's how you're just going to find that moment of inertia. Now, it isn't, I just want to point out that got typed up. It's like, come on. It's like 2/3 mr squared. It isn't like 2/3 mr squared. Okay, it's just 2/3 mr squared. So, what you're going to do, this is like a hollow sphere. Okay, it's like a spinning ping pong ball, basically. So it's moving at 30 revolutions per minute. So you're going to find the angular momentum. So L equals I omega. So you're going to use this to find I. But what does omega have to be in? Radians per second. What did I give you? No. I gave you revolutions per minute. So 1 revolution is
2 pi.
So you're going to multiply 30 revolutions by, and then divide that by 60 seconds to get radians per second. Okay? All right? So then you're going to have I, and then you're going to have your omega. So then you can calculate L. So this thing is spinning. Okay? Spinning. So what's going to happen on 17, we're going to take a bug, and it's going to land on this spinning ball. Okay? So angular momentum has to be conserved. So what's going to happen on number 17, here's what it's going to do. You're going to have the L of the bug plus the L of the ball is going to equal the new momentum of the ball plus the new momentum of the bug. Now, is the bug part of the system to start with?
No.
No. So this doesn't contribute anything initially. This one, this angular momentum of the bug, is what you already found. You already know this answer because you found that in number 16. Okay? So you're already going to know this value. Now, here's the next part. So imagine this. Here's this spinning ball, and the bug is going to land on it. Okay? Bug's going to land on it. Do you think the bug and the ball then are going to spin at the same rate?
No. Wait, sorry.
Yeah.
Yeah, the bug's going to land on the ball, right?
On the ball.
So will the bug and the ball spin at the same rate?
Oh yeah.
So what do you think you can do over
I thought
here?
you meant the initial.
Take out an L.
Oh, it's like the California thing, right? Because the bug has landed on the spinning ball. Oh, that's kind
Now
of
it
cool.
makes sense.
Oh, it's California.
So this is going to be, this is going to sound odd, but this is going to be the eyeball plus the eye of the bug times, even better, butt prime. So you're going to know everything but butt prime. Now, I tell you to treat the bug as a point mass. So treating the bug as a point mass, you're going to use mr squared. Okay? So you got the mass of the bug, the radius of the bug. You already know the eye of the ball because you found it up above. So the only thing you don't know is butt prime. Now, when the bug lands on the ball, is it going to spin slower or faster?
Slower.
Slower. Okay, just like when two objects move off together and they do the California thing, they move off together, they slow down. Okay? So you know when you find this butt prime, it has to be smaller than your initial butt because you have more moment of inertia. When you get to number 18, you're going to find the moment of inertia of the moon as it orbits the Earth. It's going to be a really big number. Okay? And I tell you on number 18, treat the moon as a point mass. So what equation do you use for moment of inertia if it's a point mass?
MR squared.
mr squared. So on number 18, here's what you're going to do. On number 18, you're going to go, oh, L equals I omega. You're going to use mr squared here. You've got the mass of the moon, you've got the radius. You've got those numbers. You don't have omega. But do you think the moon travels at a pretty constant rate of spin around the Earth? So guess what? We can use theta over time. So how many radians is the moon going to move through in one revolution? 2 pi. Oh, that's kind of cool. How long is it going to take?
27.3 days.
27.3 days. What are you going to do with the 27.3 days?
Seconds.
Change them into seconds. So then you can find I, and then you can find your butt, and then you can find your L. So, there you go. You're on your own. All right.